Hello everyone. Today let us discuss about capacitance of a parallel plate capacitor with a conducting slab. Our topic is capacitance of a parallel plate capacitor with a conducting slab. In our previous video, we have seen a parallel plate capacitor with a dielectric slab in between the plates. But now this is a conducting slab. So let us start our discussion. Let us take a parallel plate capacitor with the two parallel plates like this, with a distance of small d between the plates, and each plate has a cross-sectional area capital A. Cross-sectional area capital A. If there is no dielectric slab or if there is no conducting slab, let us assume if there is only vacuum in between the plates, then the capacitance of a parallel plate capacitor is given by C naught is equal to epsilon naught A by D. You all know where epsilon naught is permittivity of free space. So let us first assume if there is a parallel plate capacitor, simple parallel plate capacitor with vacuum in between the plates, let capital A be the area of the plates, small d is the distance between the plates, then capacitance is given by C naught is equal to epsilon naught A by D. Epsilon naught A by D. Now, after that, our discussion is now we have introduced a conducting slab of thickness T in between the plates. You can see here, this is our conducting slab. We have introduced it in between the plates that has a thickness of D. That has a thickness of D. That has a thickness of T, small t, and distance between the plates is D. Distance between the plates is D. Thickness of the slab is small t. So with that introduction, let us see now. The upper plate has a charge of plus q and the lower plate has a charge of minus q. Distance between the plates is d. Thickness of the slab is small t. Thickness of the slab is small t. Now the plates have the charge plus q and minus q. So in general we say it is plus or minus q. Plus or minus q. Therefore, the electric field E naught between the plates of the capacitor, electric field E naught between the plates of the capacitor, E naught is equal to sigma by epsilon naught, where sigma is a surface charge density. We all know that sigma is equal to Q by A, that is charge per 1 unit area. Therefore, replace sigma with Q by A. Replace sigma with Q by A. We will get E naught is equal to sigma by epsilon naught. Sigma is equal to Q by A. Therefore, E naught is equal to Q by A epsilon naught. Let it be equation number 2. Let it be equation number 2. When there is nothing in between the plates of the capacitor, so capacitance C naught is equal to epsilon naught A by D. This is equation number 1. This is equation number 1. Now, when there is nothing in between the plates, the electric field E naught is equal to sigma by epsilon naught, that is equal to Q by A epsilon naught. Let it be equation number 2. Let it be equation number 2. Now, the potential difference between the plates of the capacitor, V naught is equal to E naught into D, that is equal to Q by epsilon naught A into D, because we know from equation 2, E naught is equal to Q by A epsilon naught. Substitute the value of E naught, we will get V naught is equal to E naught into D, but E naught is equal to Q by A epsilon naught. Substitute that value, you will get V naught is equal to Q by epsilon naught A into D. You can see this is equation number 2. This is E naught is equal to Q by A epsilon naught. That we have substituted here, and we got this V naught is equal to Q by A epsilon naught into D. Now, we have introduced a dielectric slab of thickness T here in between the plates of the capacitor, where the thickness T is less than the distance between the plates, that is D. T is less than D. T is less than D. Now, if you see that picture, clearly you can see upper plate has a charge plus Q, lower plate has a charge minus Q, distance between the plates is D, thickness of the slab is small t. Now the electric field inside that slab becomes 0. The electric field inside it becomes 0. So once again I repeat, here if you take a conductor in between the plates, the free electrons flow inside it. Therefore, field inside the slab becomes 0. The field inside the slab becomes 0. Then it develops a charge minus Q on the upper side plus Q on the lower side of the slab. Therefore, as the field inside the slab is 0, there is electric field only in the outside, no electric field inside the slab. So what we are trying to understand here is, this is a conducting slab, this is not a dielectric. Therefore here free electrons are flowing. Therefore there is no electric field. Electric field becomes 0. Therefore it develops charges minus Q on the upper side and plus Q on the lower side. You can see here plus Q on the lower side of this particular slab. Now because in this slab the electric field is 0, there is electric field only outside the slab. Outside the slab means in a distance of D, for a thickness of T, there is no electric field. For a thickness of T, there is no electric field. So where there is the electric field is only for a distance of D minus T. I hope you are understanding. Full thickness of this slab is T. This is the distance between the plates is D, and the thickness of the slab is T, but within the thickness T no electric field. So where the electric field, it is only for a distance of D minus T. Therefore the potential, the electric field is only for a thickness of D minus T. Therefore the potential difference V is equal to E naught into D minus T. We have to take the electric field only for a distance of D minus T. That is from equation 2. Equation 2 means this is equation 2. From this equation 2, you know E naught is equal to Q by A epsilon naught. E naught is equal to Q by A epsilon naught. Therefore, here you substitute that E naught as Q by A epsilon naught, then you will get V is equal to Q by A epsilon naught into D minus T. Let it be equation number 4. Now, capacitance of the capacitor with conducting slab in between the plates, C is equal to Q by V. This is the standard relationship which we have been seeing from long back. C is equal to Q by V. Therefore, C is equal to Q by V. In place of V, we will substitute equation 4. Equation 4 means this equation. we will substitute V is equal to Q by A epsilon naught into D minus T. We will substitute that. Therefore, you will get C is equal to Q by V. In place of V, we have substitute equation 4, Q by A epsilon naught into D minus T. Therefore, in this particular equation, Q and Q will be cancelled. A epsilon naught will go up, and therefore you will get A epsilon naught into D minus T. Let it be equation number 6. Here Q and Q are cancelled. Then you will get C is equal to epsilon naught A by D minus T. Up to that we got now. Then next what we will do, let it be equation number 6. We will multiply this equation 6, that is numerator and denominator of equation 6 with D. That's what we are doing here, multiplying and dividing with T. Then you will get this equation 7. And then you will get epsilon naught A by D into D by T minus D minus T. Epsilon naught A by D from equation 1, it is nothing but C naught. That is capacitance of a parallel plate capacitor with vacuum in between the plates. So all this will become C naught. So substitute C naught value in place of epsilon naught A by D, and it is multiplied with D by T D minus T. Therefore, what we will get finally, C is equal to, that is capacitance of a parallel plate capacitor with the conducting slab in between the plates, C is equal to C naught into D by D minus T. So clearly you can see from this equation, you can clearly see C is greater than C naught. C means parallel plate capacitor, that is capacitance of the parallel plate capacitor with conducting slab. C naught means capacitance of the parallel plate capacitor with vacuum. Now which is more? Clearly we can see the capacitance of the parallel plate capacitor with conducting slab in between the plates is greater than the capacitance of the parallel plate capacitor with vacuum in between the plates. That is, C is greater than C naught. That is, capacitance of a parallel plate capacitor with conducting slab is greater than that of a parallel plate capacitor with vacuum in between the plates. Therefore, by introducing a conducting slab of thickness T in between the plates of the capacitor, we can increase its capacitance by a factor of D by D minus T. Therefore, by introducing a conducting slab of thickness T in a parallel plate capacitor, we can increase its capacitance by a factor of D by D minus T. So finally, this is the expression for the capacitance of a parallel plate capacitor with conducting slab in between the plates. So it is increased by a factor of D by D minus T. Thank you for watching this video. We will meet with another video with another topic. We will meet in the next video with new topic. Till then, bye. God bless you all.